What if falling into a black hole doesn't mean the end, but the beginning of something else? For centuries, we've stared into the dark, searching for answers to the most terrifying question in the cosmos. What happens when the universe collapses in on itself? A black hole is not just destruction, it's transformation. It's the ultimate paradox, a place where time stops, space folds, and everything we know about physics breaks apart. It is, in every sense, the universe's greatest mystery, and its most beautiful nightmare. Imagine drifting through the silent sea of stars. The light of distant suns flickers around you. Then, ahead, a region of space where the light itself seems to vanish. No reflections, no glow, just a perfect, endless shadow. That is the edge of a black hole. The event horizon, the point of no return. Once you cross that line, there is no way back. Not for matter, not for light, not even for time itself. But what lies beyond that horizon? Is it truly the end? Or could it be the beginning of something far stranger? Let's start from the beginning. Black holes are born from death. When a massive star, far larger than our sun, exhausts its nuclear fuel, it begins to collapse under its own gravity. This core, unable to resist the inward pull, implodes in a fraction of a second. The outer layers explode in a brilliant supernova, lighting up the galaxy like a cosmic firework. But what remains after that explosion is something much darker, a singularity, an infinitely dense point, where all the mass of that star is crushed into a space smaller than a grain of sand. Gravity here becomes absolute, so strong that it curves space and time into a funnel so deep that not even light can escape its pull. And that's why black holes are black, because they let nothing out. They are not objects we can see. They are regions we can only sense by watching how they twist and bend everything around them. Astronomers can't photograph the black hole itself. What they see is its shadow, a silhouette surrounded by a glowing ring of light, the last radiation escaping before falling in forever. That glowing edge, that fiery halo, is the event horizon. To the outside observer, anything approaching the event horizon appears to slow down. As it gets closer, it seems to freeze in time, its light redshifting until it fades into darkness. But to the object falling in, nothing seems to stop. Time flows normally. It crosses the horizon and continues its fall into the unknowable interior. This strange contradiction is one of the most haunting features of black holes. Time behaves differently depending on where you are. Einstein's general theory of relativity tells us that gravity bends not only space, but time itself. Near a black hole, time stretches like elastic. An hour for the falling object could be 1,000,000 years for someone watching from far away. In a sense, black holes are natural time machines, not in the way science fiction imagines them, but in the way reality truly works. They distort the flow of existence. When you stand at a safe distance from a black hole, you're looking into a window of frozen moments, matter and light trapped in eternal descent, forever falling but never reaching the end. Yet, to the matter itself, is a journey beyond comprehension, a one-way trip into infinity. For decades, physicists believed that anything crossing the event horizon would be destroyed instantly, crushed by infinite gravity at the center, in a place called the singularity. But as our understanding deepened, a new question arose. What if the singularity isn't an endpoint at all? What if it's a bridge, a doorway to somewhere else? Inside the equations of general relativity lies a strange mathematical possibility. Wormholes, tunnels connecting different points in space and time, and at their heart, the same structures that define black holes. Could a black hole actually be the entrance to another universe? A cosmic tunnel leading to a new beginning? We don't yet know, and perhaps we never will, because no information can escape from beyond the event horizon to tell us. But one thing is certain: black holes are not just the monsters of the universe. They are its engines. They shape galaxies, drive cosmic evolution, and sculpt the very fabric of spacetime. At the center of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, millions or even billions of times heavier than the Sun. Ours is called Sagittarius A*, and it quietly anchors everything around it. Stars orbit it, gas spirals into it, and somehow it holds our galactic home together. Without these cosmic giants, galaxies might never have formed as we know them. It's strange to think that everything we see, every planet, every star, every atom that makes up you and me, exists because of something that devours light. The destroyer is also the creator. As we drift closer to the edge of the black hole, the universe around us begins to stretch. Light bends, stars twist into streaks, and the calm blackness of space starts to ripple like liquid glass. You are approaching the event horizon, the point where gravity becomes so powerful that not even the fastest thing in the universe, light itself, can escape. This is the most mysterious boundary in existence. To cross it is to step outside the rules of our reality. Physics, as we understand it, stops making sense here. But let's imagine you could survive the fall. Let's imagine you could see what lies beyond. You pass through the event horizon. To you, nothing dramatic happens at first. There's no explosion, no tearing apart of your body. Space seems calm, eerily quiet, but something has changed. Behind you, the entire universe has vanished. Every photon of light, every sound, every memory of where you came from, all sealed beyond a one-way wall. From this point on, your path only goes forward. The gravity becomes irresistible. You are pulled not just through space, but through time itself. Every second you fall deeper, you move closer to the heart of the black hole, toward the singularity. What is the singularity? According to Einstein's equations, it's a point of infinite density, a place where matter is crushed into zero volume, and spacetime curves infinitely inward. In that moment, everything we know, the laws of physics, energy, matter, light, even the concept of space, ceases to exist. It's not just the destruction of matter, but of meaning itself. But infinity is a word scientists don't trust easily. Infinity usually means something is missing in the math, a clue that the theory we're using is incomplete. And that's what black holes reveal. Our understanding of reality is still unfinished. Einstein's general relativity describes gravity perfectly on large scales. Stars, galaxies, the universe itself. But when you zoom in to the smallest scales, atoms, quarks, the quantum world, it breaks down. At the heart of a black hole, these two worlds collide. The infinite gravity of relativity meets the chaotic uncertainty of quantum mechanics. And they don't agree. This clash of laws is called the information paradox. It's one of the most important puzzles in modern physics. Here's why it matters. According to quantum mechanics, information, the pattern of what makes up matter and energy, can never truly be destroyed, can change form, scatter, or transform, but it must always exist somewhere. Yet inside a black hole, everything that falls in seems to vanish forever, destroyed, erased from the universe. That can't be right. If black holes destroy information, then the fundamental laws of physics collapse with it. So where does the information go? For decades, scientists have wrestled with this question. Stephen Hawking believed that black holes slowly evaporate over unimaginable timescales, emitting faint radiation now known as Hawking radiation. Tiny particles escape from the edges, as if the black hole were whispering its secrets into the void. Over time, billions, even trillions of years, the black hole shrinks, fades, and disappears entirely. But what happens to the information it once held? Does it escape with the radiation? Or is it stored on the black hole's surface, encoded somehow in its event horizon? In 1997, a revolutionary idea emerged, the holographic principle. It suggests that all the information about what's inside a black hole might actually be projected on its surface. Like a hologram, the event horizon isn't just a boundary, it's a cosmic hard drive, recording everything that ever fell in. Every atom, every photon, every detail of the universe. etched into a thin layer of light and gravity. It's a mind-bending thought that a three-dimensional reality could be described entirely by information on a two-dimensional surface. If true, it could mean that our entire universe is a kind of hologram, a grand projection from the edges of space and time. But even deeper questions remain. What lies at the singularity? Does space simply end? Or does it fold into something else, a tunnel, a bridge, a doorway? Mathematically, Einstein's equations allow for such tunnels. They're called Einstein-Rosen bridges, better known as wormholes, shortcuts connecting distant parts of the universe, or even different universes entirely. A black hole could, in theory, be one mouth of such a bridge. If something could pass through the singularity, it might emerge elsewhere, in another galaxy, another time, or another reality altogether. But here's the catch. The immense gravitational forces near the singularity would rip apart any matter long before it could cross. No spacecraft, no atom, not even light itself could survive. So if wormholes do exist, they may remain forever hidden, theoretical doorways we can never open. Still, the idea refuses to die. In the quiet halls of physics labs, scientists continue to search for a theory that unites the large and the small. A single framework that explains both gravity and quantum mechanics. This quest is known as quantum gravity, and it might hold the key to unlocking the truth about black holes. Perhaps the singularity isn't infinite after all. Perhaps it's a region where space and time are quantized, where the universe folds back upon itself, and new realities are born. Some theories even suggest that every black hole could give birth to a new universe inside it, a cosmic seed expanding beyond our perception, with its own space, time, and laws of physics. In that case, our own universe might have been born from a black hole, in another, older cosmos, a universe within a universe, creation born from collapse, life emerging from death. The deeper we go, the more black holes seem less like endings, and more like mirrors reflecting the universe's deepest secrets. They are the places where the cosmos hides its blueprints, where reality folds in on itself to ask, "What am I?" Imagine drifting beyond the event horizon, that invisible veil where light itself bows in surrender. Space no longer behaves the way we know it. Distances stretch, time slows, and the rules that once felt absolute begin to dissolve. From the outside, it looks like you're frozen, suspended in time. But from your own perspective, you're still moving deeper, closer to something both terrifying and beautiful. Here, gravity doesn't just pull, it twists. It shapes reality into something unfamiliar. You might picture stars smeared into luminous ribbons, light bent around you into strange halos. Every direction leads inward. Every movement feels guided by an unseen hand. And somewhere ahead lies the singularity, the heart of the black hole, where physics as we know it breaks apart. But what is the singularity, really? For decades, physicists have debated that question. According to Einstein's general relativity, it's a point of infinite density, a place where space and time curve so sharply they collapse into a single, dimensionless point. All the mass that once formed the star millions of suns worth, compressed into an infinitely small volume. The equations predict that, at the singularity, the known laws of nature simply stop working. Yet many scientists believe this idea of an infinite point is just a sign that our understanding is incomplete. It's not that infinity exists in nature, it's that our equations break down before we can see the real truth. To truly understand what happens inside, we'd need a theory that unites the two great pillars of physics: relativity and quantum mechanics. Relativity describes the universe on the grandest scales: stars, planets, galaxies, spacetime itself. But quantum mechanics rules the microscopic, atoms, particles, and the strange dance of probabilities that govern their behavior. Inside a black hole, both realms collide. Gravity becomes unimaginably strong, and matter is crushed to quantum scales. Yet relativity and quantum theory refuse to play nice together. Where one predicts smooth curvature, the other demands jittering chaos. Somewhere inside the event horizon, they clash, and we're left without answers. Some physicists suspect that the singularity isn't really a point at all, but a region of exotic quantum geometry. In these depths, spacetime might not be continuous but granular, built from tiny, discrete quanta like pixels in a cosmic screen. This idea emerges from theories like loop quantum gravity, which suggest that spacetime is woven from tiny loops, preventing it from collapsing infinitely. Instead of a singularity, there might be a bounce, a kind of rebirth where matter is compressed, transformed, and then expands into something new. Could a black hole, then, be a doorway? Not just to destruction, but to creation. That's where one of the most fascinating ideas in modern cosmology enters: the black hole cosmology hypothesis. It proposes that each black hole might give birth to a new universe. Imagine, for a moment, that beyond the singularity lies a tunnel, a passage that leads not to oblivion, but to a fresh Big Bang, where new space and time burst into existence. From our perspective, everything that falls in vanishes forever. But from inside, a new cosmos may be expanding, with its own galaxies, stars, and laws of physics. In that case, our own universe might have been born from a black hole inside another universe. A cosmic nesting doll, each layer giving birth to the next. It's an idea both poetic and humbling, the thought that the violent death of one world could be the quiet birth of another. Still, even this doesn't solve all the mysteries. There's another problem, one that haunted Stephen Hawking for decades: the information paradox. According to quantum theory, information, the fundamental description of a system, can never be destroyed. If you burn a piece of paper, its atoms scatter, but in principle, the information about their arrangement still exists in the smoke and ash. But when something falls into a black hole, that information seems to vanish. The object's identity, its atoms, energy, structure, disappears beyond the event horizon. If the black hole later evaporates through Hawking radiation, that information would be gone forever. And that violates one of the most sacred laws of quantum physics. To resolve this, Hawking proposed something remarkable: that information might not truly be lost, but somehow stored on the black hole surface. Imagine the event horizon not as a smooth boundary, but as a cosmic hologram, a two-dimensional sheet encoding everything that has ever fallen inside. The three-dimensional interior we imagine may be an illusion, projected from this thin surface of data. This is the essence of the holographic principle, a concept that has reshaped how we think about space, information, and reality itself. If that's true, then the universe itself might work the same way. Everything we experience, stars, galaxies, even our own thoughts, could be a projection of deeper information inscribed on a distant cosmic horizon. We might be living inside a grand hologram. It's a dizzying thought, one that stretches the boundaries of science into philosophy. But black holes seem to demand that we think this way. They challenge our sense of what's real, what's observable, and what can ever be truly known. The deeper we go, the more it feels as if the universe is hiding its secrets in plain sight, daring us to look closer, even as it blinds us with its brilliance. And yet, maybe that's the point. Maybe black holes exist not just as cosmic graveyards, but as mirrors, reflecting back our own curiosity, our relentless drive to understand. Because when we stare into that endless darkness, it stares right back. And in that reflection, we see the infinite questions that make us human. So maybe falling into a black hole isn't really about endings at all. Maybe it's about perspective, about realizing that every collapse, every moment of darkness, might just be the beginning of something new, something unseen, yet waiting to unfold. From the outside, a black hole is silence and shadow. But within that darkness, hidden beyond the event horizon, might lie the story of creation itself, written in the language of gravity, time, and light. It reminds us that the universe is not a simple place. It's a living mystery, a vast conversation between matter and meaning, between what we can see and what we can only imagine. Perhaps, in the end, black holes are the universe's way of whispering, "You don't know everything yet." And maybe that's the most beautiful truth of all. So the next time you look up at the night sky, remember, those tiny points of light, scattered like dust across infinity, are more than stars. Some are windows into places where time stands still, where reality folds in on itself, and where the universe hides its deepest secrets. Sleep well, dream deeply, and never stop wondering what lies beyond the event horizon.